Hello folks, I am back to do the second half of the lecture. I decided to make two separate videos just in case the first one didn't work, but it looks like we're back in business. So I am picking up on the top of page 10 inside this example one within generalized linear models. This week just focusing on linear models. So the logic that has required me to demonstrate linear models in a class that has that as the prerequisite is that I really want to make sure that folks are comfortable with all of the things that I need them to be able to do on the X side of the model. So being able to get additional f-tests, being able to get additional slopes that are linear combinations of the fixed slopes being provided by the model, being able to generate predicted outcomes from the model, all of those things that we just went over in the last video, I really want to make sure that folks are able to do. Adding to that list then, I really want folks to be able to understand what to do with an interaction term, because these concepts persist no matter what kind of y you're going to eventually be predicting. So the rest of the class is focused on messing about with the y side. For instance, next week we'll start talking about predicting binary y outcomes instead. For today, we are going to be focusing on the x side still. So at the top of page 10 here, I'm going to go through this by program again, as I had said earlier, so that folks who are not interested in each program can skip ahead if they want to. Here's the new model that we're going to be working with for this example. It corresponds to equation 2.9 in chapter 2 of my longitudinal analysis book. This is the new term. So this is an interaction between quantitative age and grip strength. It would be added to answer a question of moderation, such as, does the effect of age depend on how strong you are? Or, does the effect of physical function vary by age? So each of those in the context of a moderation hypothesis addressed via a two-way interaction is equally valid. Mathematically, there is no difference between which variable is considered the predictor and which is considered the moderator. The difference is entirely in interpretation. And oftentimes research questions and research contexts are going to lean you towards one side more than the other, and so it can be more convenient or intuitive to think of one as the moderator and one as the predictor, but I will show you how to work with them from either perspective so that you will have a better sense of how these interaction terms function. So here's my new model. Same data, example 1 still. Here's the interaction term. So when you're using ProcGLM in SAS, as well as general linear models in a lot of programs, you do not need to define a variable for the interaction term ahead of time. In classic regression software and including ProcReg in SAS, I would have had to have made a new variable that is literally the multiplication of these two variables and add that to my data set. You do not need to do so here. So you can create interaction terms on the fly by defining them using this star and asterisk. So the rest of this for right here is just as we had before in the main effects model. I'm asking for the non-given but model implied difference between the two alternative groups, how future and current differ from each other, as well as the omnibus main effective group. And then here's an additional contrast that I include just as an example to make the point that you can lump together any kind of slopes that you want to or need to. So this type of idea takes the place of what is referred to as hierarchical regression. So it used to be the case that you would put in, say, a couple predictors in one block, and then you would add a set of new predictors in a second block so that you could see how much the R-square increased by that new set of predictors and get an f-test for that increase. This contrast statement does that for you in one model. So the result of this contrast that I'm getting from lumping age, grip strength, and their interaction would be the same f-test as if I had added those three effects second in their own block. So you can ask for any model subset, like what would happen if these terms weren't here from the same model. So this is going to give me an f-test for the joint contribution of age and grip strength and their interaction as an example. This is going to give me predicted outcomes for my fake people. So this data set has the same 9 fake cases added to it that I demonstrated from the main effects model, so that I can easily obtain predicted outcomes for those 9 cases. Because those 9 fake cases do not have a real outcome variable, they are not going to mess anything up. They will not be used in the estimation of the model. They will only be used in this subsequent command to create columns for the predicted outcomes and the standard errors. So these predictions will occur for every case in the dataset, real or fake. I'm using the fake people so that I can take those predictions and plot them. So now the new stuff. Understanding interaction terms involves understanding how the new interaction adjusts its constituent main effects. So we can talk about how the effect of age differs by grip strength, or how the effect of grip strength differs by age. So let's do that. So the process for figuring out how the model says any given slope is created as a function of its interacting predictors requires you to go up to the equation, find all of the terms that have the slope of interest. So if I want to get the age slope, then I need beta 1, and I also need beta 6. So that's brought down here. The next step, after you find all the terms that involve the slope of interest, which is age here, is to factor age out. So we're trying to create a term that is eventually going to multiply age as a variable, and the term after you factor age out is this right here. So these are the ingredients that allow us to now ask the program to estimate what the slope is, conditional on particular values of grip as the moderator. So I'm going to demonstrate this for values of 6, 9, and 12, which is roughly plus or minus 1 standard deviation and the mean. So this age 85, again, does not refer to the variable in this context. It refers to the beta. So what I am saying by age 85.1 is, I'd like one of these, please. I need one beta 1, because at a minimum, that's what's going to give me the slope of age. So all slopes of age have to start with that at a minimum, or else it's not the slope of age. Then the question is, okay, what else do I need conditional on grip? So if I want the slope of age for somebody with a grip of 6, then I plug in minus 3 for the interacting moderating variable's value. So the minus 3 is the term that goes in here. Likewise, if I wanted to get a prediction for grip of 9, I put a 0 here. So this line really is only here for pedagogical purposes because that is what beta 1 already represents. Beta 1 is the age slope when grip equals 9 because that's the part where this term drops and you're left with just beta 1. So this isn't actually a linear combination, but again, it's here to demonstrate the logic of the process. And then likewise, if I want to have grip equals 12, I put a 3 here. To do the opposite, let's say that I want the simple effect of grip. Same process. Go up to the equation, find all the terms that have grip in them somehow. Bring those terms down. Factor grip out because that's the variable we want the slope for, and the term in brackets is the linear combination that creates the grip strength slope as a function of age. So grip 1 here means I need 1 beta 2, because I always need at least beta 2, otherwise it's not the grip strength slope. And then I need to specify the value of age for which I want the grip strength slope. So age as the moderator, grip as the slope. And so now the value that I put in behind the interaction term is consistent with age. So this is what's potentially confusing about this process, is that if you look up here and look down here, it's the same interaction term, but it's doing different things. Up here, when we're estimating the age slope, minus 3 refers to the value of the moderator grip. Down here, when we're estimating the grip slope, minus 5 refers to the moderator value for age. So it's really helpful in your head to think about having extracted grip from all of these terms and seeing what you're left with. Age is the only variable that is relevant to include values for right here. So minus 5, 0, and 5 corresponds to 80, 85, and 90. And just as we didn't need the middle one up above, we don't need it here either, because this is already what beta 2 tells us, what the effective grip is at the centering value for age. Last but not least, if you're not using fake people and you wanted to create predicted outcomes, you would need to write separate statements like this. So these estimate statements necessarily look different than the ones up here because the ones up here are estimating slopes, whereas the ones down here are creating conditional outcomes, or y-hat values as they're called. So I need to use everything in the model equation to create a predicted outcome. So I need at a minimum an intercept because beta 0 is always in a predicted value. So I need one beta 0, and then here, after that, these are the values that are the multipliers for the predictor. So this is going to give me a predicted outcome for age 80. This one's going to give me a predicted outcome for grip strength 6. And if I multiply -5 and -3, that's where I get the value of 15 out here. So this looks a bit different than this does because nothing has been factored out here like it has up above in the slopes. So because I did not include any values as multipliers for the sex predictors and the dementia group predictors, they are held to 0. So this is my predicted outcome specifically for a man without dementia who is 80 years old and has a grip strength of 6. I don't have to show what it would look like as a function of sex and dementia in this model because those are just main effects and they do not interact with age or grip, so they would not change the pattern of how the effect of age differs by grip or the effect of grip differs by age. So here's my output. In my new model, we went over this in class, so I will do so here. First step, trying to think about what things are conditional in the output and what things are not. So for the intercept, although the value of the intercept for beta 0 has changed, who it refers to has not. Relative to the previous main effects only model, we have not introduced any new conceptual predictor values. We have simply refined what the predictor values are doing. So 29 is still the expected cognition for an 85-year-old with 9 pounds of grip who is a man and who does not have dementia. Likewise, this effect of sex is a unique marginal effect. So in the taxonomy that we introduced a few classes ago, the word unique means after controlling for the other predictors. So that will always be true so long as you have at least 2 predictors in your model. Each slope is going to control for or condition on or hold constant or whatever you want to call it, the other predictor slopes in the model. So this is the gender difference controlled for dementia, age, grip, but it's the gender difference for everybody. That's what marginal means. So sex does not interact with any other predictors in this model. That means the model says this is the sex difference for all people, regardless of age, grip, and dementia. Likewise, these dementia variables do not interact with anything, so they are also unique marginal. These are the expected dementia group differences, and they will be the same amount of difference regardless of age, grip strength, and gender. So then we get to these ones. Because age and grip are part of an interaction term, each of these main effects is a conditional main effect, or a simple main effect, or a unique conditional in my taxonomy. It's the idea that you can't just talk about these as the slope of age or the slope of grip and go home. You have to say who they are the slope for. So more specifically, if I were to interpret this slope of age, I would say that for every year older you are, cognition is expected to go down, so there's a negative sign, it's going to decrease, by 0.33, and that effect of 0.33 decrease holds specifically for somebody with 9 pounds of grip strength. Likewise, the opposite direction. This is the slope of grip, so for every pound stronger you are expected to have greater cognition by 0.6, specifically in 85-year-olds, because that's the only point where this interaction term does not apply. So then to talk about what the interaction term does, a common mistake is to try to talk about what happens to y as a function of both of these variables at once. Don't do that. It's much easier to think about which of the 4 kinds of interactions do I have, because every interaction does one of 4 things. It makes a main effect more positive, less positive, more negative, or less negative. So if we start with the main effect of age up here. The main effect of age is negative if grip is 9. What the interaction term does to it, because it's positive, is make that effect of age less negative as grip increases. More specifically, the coefficient for the slope of age is minus 0.33 if grip is 9. For every additional pound of grip strength, that age slope becomes less negative by 0.12. So the slope of age changes by 0.12 per pound of grip as the moderator. So less negative or less positive both indicate weaker slopes. The effect is moving closer to 0 as grip increases. So if I were to put this into more intuitive terms, so after I explain the results in a results section, for instance, you owe the reader a subsequent sentence that puts it into better context, I might say something like, the negative effect of age is weakened in stronger people, or the effect of age is buffered by going to the gym. Haha, that's not actually true, but let's go with that. I can tell you that firsthand. If you're old and you go to the gym, you might be more likely to hurt yourself, but that's another story for another day. So whenever you have the interaction and a main effect being opposite in sign, they're working against each other. So that's a less negative or a less positive. The other possibility is demonstrated by starting with the main effect of grip and then talking about what happens to that grip slope as a function of age as the moderator. So the grip slope is 0.6, so that is the change in cognition for a 1 unit change in grip in an 85-year-old. That positive grip slope is going to become more positive by 0.12 per year of age. So the coefficients are in the same direction, so they are working together. So we would say that grip matters more if you're older than if you're younger. So age enhances, magnifies, exacerbates, whatever you want to call that. It is an over-additive interaction combination. So you can choose in a given analysis which of those 2 interpretations is more useful to you, but they're both valid. So then the rest of the output is helping to clarify, refine when does age matter and when does grip matter. So then we get the simple slopes output that we requested. So this is the main difference from dementia. It's pretty much the same as before. I want to draw your attention to these results right here. So these are the specific age slopes at the chosen values of the moderators, low, medium, and high. So the middle rows are the ones that were already given to us to the model by the model. So what we find then is at grip equals 6, there is a significant negative effect of age. At grip equals 9, there is still a significant negative effect of age. But by the time you hit grip equals 12, the effect is not different than 0, and it is actually flipped into the positive direction. So somewhere between grip strength of 9 and grip strength of 12, age stops mattering. Likewise, if I look at the grip strength slope at 80, it's positive but non-significant. At 85, it is positive and significant, and it continues to get more positive as age increases. So somewhere between age 80 and age 85, the grip strength slope stops mattering. So in situations like these, rather than doing this pick a point, let's see if it's significant here, is it here, is it here, it can be more useful instead to try and compute the ranges of the boundary, the boundary and the ranges of the moderator variable at which the predictor slope is significantly positive, non-significant, and then significantly negative. And then you can compare those ranges to the distribution of the moderator in your sample, and you can talk about sort of what percent of your sample has a positive slope and what percent of your sample would have a negative slope. I do that in chapter 2 of my book where these data are described. The idea is called regions of significance, and I will have a demonstration of that in a little bit after we go through the results in the other programs. And then here are the predicted outcomes. I can then make a picture of them. And so then here's the moderation shown from both perspectives. On the left, we have how age matters as a function of grip. So in people who are stronger, that's the top line, age matters less. It matters more in weaker people. And likewise, grip strength matters less in older people, that's the green line, and it matters more in older people, it matters less in younger people. Okay, moving on to Stata then. Same story, different code. So these commands are all the same as above. I lost my D here somehow. Let me put that back in. This is a new F-test to demonstrate the idea that you can lump together any slopes that you want to. So in this case, I've created a joint hypothesis test for the combined effects of age and grip strength in your interaction. This would be analogous to fitting a hierarchical regression model in which those terms are not included, and then adding them as a second block in order to judge the change in the R-square. This approach allows you to essentially do any combination of hierarchical regression you want to, but do it within the same model. So this is a test of what would happen if those terms weren't included. So it's telling us what is being added by those three terms jointly. Then we get to the simple slopes. So if I want to know how the model predicts the age slope for any person, I go up to my equation. I find all the spots that have age in them as my target slope. I bring them down here. I factor out age, and then what's left in the brackets is the slope according to the model for age as a predictor. So it's a function of grip strength. The Lin-Com statements down below then provide simple slopes at particular values of grip as the moderator. So this age 85 times 1 is saying at a minimum I need a beta 1 because I have to have that in order for this to be an age slope. Then the question is, what else do I need as a function of the moderator grip? And here I fill in a -3 because what I'm trying to estimate is the grip strength slope at 6 for grip. Or age slope at grip equals 6, sorry. Can't screw that up. Still on the age slopes in this section. So this is the multiplier, the -3, that goes in the parentheses here. It conditions the age slope on grip strength. The middle line is not actually necessary. It's here for pedagogical purposes because this is the effective age at grip equals 9, which is already given to us by beta 1. So we don't actually need a linear combination for that. That's when the interaction term drops. And if I want grip at 3 instead, then I can throw that here. Much like how Stata has a shortcut to get predicted outcomes over a range of values for the predictors, it has a similar shortcut for how to get simple slopes over the range of a moderator. That is a sub-option within margins called dy dx. So the derivative of the function with respect to x. So I'm trying to ask, I want the age slope, who do I want it for? In grip strength starting at -3 in increments of 3 up to 3. So this one line of code replaces all 3 lines. I still think it's instructive though to show the 3 lines as evidence of what is actually happening under the hood when you use this dy dx command. But once you understand that, it can be much more convenient to specify simple slopes for any value of the moderator at the same time. Likewise, so if I take the interaction and flip it around and say that I want to look at what the effect of grip strength is for any age, same process. Go up to the model, find all the terms that have grip in them, bring them down here, factor out grip because that's what I want the slope for. The terms that are left in the brackets is how the model says the grip strength slope is computed for any age. So now grip strength 9 times 1 means at a minimum I need 1 beta 2. Because that is the starting point for forming the grip strength slope. Then the question is, what else do I need as a function of age? So that's where I have the interaction term. And if I want it for age 80, then I plug in -5 here as the multiplier of the interaction term. And I forgot to mention a minute ago that in order to add interaction terms on the fly without having to define a new predictor variable in the data set, you can do so in Stata by adding this thing, which is either a #sign or a hashtag, depending on how old you are. So that's what this little jobby here does. And then likewise, you can use dy dx to replicate these 3 lines. So I'm getting the grip strength slope at a range of ages specified here. And I can ask it to generate predicted outcomes and to make plots of those predicted outcomes and save them. And so that's where those plots came from out of Stata. All right, moving on to R then. So for those of you who are just joining us who have fast forwarded to get to R, we're working with a model in which we have added a new interaction term of age by grip. So I have added that in R to the call under the formula piece here, and in R to add an interaction term on the fly without having defined a predictor variable for it already. You just need a colon. So that will create an interaction term. A couple things that I have learned the hard way about specifying interactions in R. Whether you want it to or not, it is going to stick an interaction term after all of the other main effects in your model. So it's helpful just to write it after, even if you want it someplace else, because it's not going to listen to you. And also, it does not appear to understand the interchangeability of a two-way interaction. So because age is listed first, followed by grip, the interaction term has to be listed this way. There were a few errors in my code where I had written grip by age at various points in the syntax that follows, and I'd gotten errors and figured out that, oh yeah, it doesn't understand that those are the same thing. So be consistent in how you specify it here, because that will make the resulting code using these fixed effects much less likely to be screwed up. So I am doing the same thing as before. I'm saving these results as an object called model age grip. I'm asking to print the model and get the residual variance. I'm asking it to find the missing dementia group contrast from before, as well as the joint hypothesis test of the two slopes that create dementia group differences. And then I am adding in a separate f-test here to demonstrate the idea that you can lump together any slopes that you want to create a hypothesis test. So this third instance is creating a joint f-test for the effects of age, grip, and their interaction term. So you can do this to replace what used to be known as hierarchical regression. So in that process, people would enter a set of predictors in one block, check the R-square, then add a new set of predictors in a second block to get the change in the R-square from that set of predictors. You don't actually have to do that in two separate models. So this glht command functions similarly to say, what would happen if those three fixed effects weren't here? So essentially the f-test will tell you how much worse the model would get without them, which is the same information as how much better the model gets with them. So you can use one model and you can subset it indirectly with all of these different glht commands. So simple slopes time then to try and describe the interaction term. So this interaction term right here we can think about as how the effect of age differs by grip strength, or how the effect of grip strength differs by age. So I'll show you how to get simple slopes from both of those perspectives. First, for the age slope, the process is go up to the model equation, find all the terms that have age in them, bring them down here. Okay, so this is where we're at. These are all the terms that have age. Then we factor age out because that is the predictor we want the slope for. And what's left in brackets is how the model says the age slope gets created as a function of grip strength as a moderator. Likewise, if I wanted to go the other way and talk about how the model predicts the grip strength slope for any age, I would have to go up to my equation, find all the terms that have grip, because that's the thing I want the slope for this time. Here they are. I would factor grip out as the variable I want the slope for, and then what's left in the brackets is the linear combination needed to get the grip strength slope for any age. So at a minimum, I need a beta 2, and then what else I need depends on what age I want the grip strength slope for. So these commands down here then are going to provide me with the simple slopes of each predictor conditional on the other predictor as the moderator, where again the order of these coefficients corresponds to how it wants the fixed effects to be ordered, not necessarily how you wrote them. So that's why I have written them in this order. I put the 1 here to remind myself that that goes first. I have the interaction term last because that's where it's going to put it whether I want it to or not. So then down here, I don't need the intercept in order to get an age slope. I do need to get the effect of beta 1, so I need 1 beta 1, so 1 is the multiplier for that. I don't need to do anything with respect to grip as a main effect because that has nothing to do with age. I don't need sex or dementia group. I do need the interaction term. So then the multiplier minus 3 is what's going inside the parenthesis here. So minus 3 times beta 6 is going to give me the other piece that gets me to the age slope for grip strength equals 6. So these first 3 lines are structured the same because they're all starting with beta 1 for the age slope and then how that age slope differs by grip. Likewise, the next 3 lines are all starting with grip, so they start with beta 2, and then the multipliers for the interaction term correspond to the values of age as the moderator this time. And if you're like, yeah, that's a lot of code, is there a way to do that faster? Of course there is. Once you understand this tedious process and you're looking for a shortcut, R has many different packages that will happily do this for you. I found one called Simple Slopes within the Reg Helper package that seems to work pretty easily. I am asking for these 6 lines within this call right here within this list. And so simple slopes tests then are provided for each combination at 8 of the grip strength slope at this age and then the age slope at this list. So it works out. If you're not using fake people or the predict function, this is how you would create predicted outcomes as a function of the interaction model. So the zeros here indicate that we are holding constant gender for men and dementia group for none. And then we need a fixed intercept at a minimum. So we need beta 0 to create a y hat for everybody. Then we need whatever values of the predictors we want this predicted outcome for. So minus 5 if we want it for an 80-year-old, minus 3 if we want it for a grip equals 6, and then minus 5 times minus 3 gives us the 15 out here. The easier way to do this is to use the fake people that we created in the context of the main effects model and ask it to predict outcomes for them using the predict function. So that's what it's doing here. It's taking my fake people data set from before. It is adding a new column called y hat age grip, and that column is using the predict function from the model and doing it to just those fake cases. So then I can take that fake people information, throw it into this plotting code, and make the same pictures that I got out of Stata and SAS. And lo and behold, there they are. So it worked. All right, one last thing. I'm not going to ask you to do anything related to this on homework, but I want you to have seen it in your lives because I feel like it's underused yet very useful. And I added an article to your reference list about this, a recent paper that had a lot of resources available in it, and so I want to show you the resources that I have made available to do the same thing, the idea of regions of significance. So if we look at these pictures as a starting point, it looks like there's a significant effective age for the blue line, it looks like there's a significant effective age for the red line, but by the time we get to green, it's pretty much flat. And likewise, it looks like there's a significant positive slope for grip for 90-year-olds. I think it's still significant for 85-year-olds from the model, but by the time we get to 80, it's not significant. So we can find out where specifically each of these slopes shuts off, so to speak, where it transitions from significant to non-significant. And if we follow the arc of these different lines, eventually, like if we kept doing like grip equals 13 and 14 and 15, the slope for age would end up positive. So each of these slopes has a range of the moderator in which it would be significantly negative, non-significant, and significantly positive. And the same is true over here for the positive slope. If we kept going down, if we kept going into younger and younger ages, this slope would eventually turn negative as well. So the idea of regions of significance is, well, let's just find the boundaries at which these slopes are predicted to transition, and we can compare those boundaries to how many people are in each of those ranges in our data set. And so then we can think about, like, for what proportion of our sample is the effective age significantly negative, for instance, and for what proportion of our sample is the effective grip strength significantly positive. So that's a much more, I feel like, general and useful approach than picking these arbitrary points on a continuous predictor at which to evaluate simple slopes. So let me show you how to do that. In SAS, to do this, to get the information that you need to do this, there's one additional piece of output that's not available in GLM, but it is available in Proc Mixed, which does general linear models as one of its possibilities. If you specify the method equals residual maximum likelihood, that's the same thing as ordinary least squares. So the extra piece then is this right here. Cov B gives us the asymptotic covariance matrix of the fixed effects. So this is not what you're used to thinking about in terms of covariance. It is a matrix in which the predictor slopes are being characterized. So their standard error squared, their sampling variance, is on the diagonal, and then the covariances among the slopes are on the off diagonal. And so to do this, we need to get the covariances among the slopes and the interaction terms. So I'm asking ProcMix to save this new table as a piece of output because I wrote a macro program by which to compute regions of significance for you. So this is the table that results. So on the diagonal, for instance, this is the standard error for the age slope squared. This is the standard error for the grip strength slope squared. And then these are the covariances between the interaction term slope and each of the main effect slopes. We need those numbers in order to be able to compute this. And this same output is available in the regress command instated directly with stat_vce. So that's an option that you can add that will allow you to get this table. So inside the download folder for this example, I threw in an Excel spreadsheet right here. This is from the book's website, where I have a page in the spreadsheet, so a sheet in the workbook, let's use the right terms here, that has formulas plugged in which you can plug these numbers in and compute regions of significance. I also wrote a SAS program that does this for you. So this is available in the SAS syntax file online. You don't have to do anything to the program other than just run it. And this is the call to it. Inside the code, it tells you what each of these arguments means. But this is allowing me to get the effective age as a function of grip as the moderator. And after I run this call, this is the output that it creates. So it tells me the values of grip strength at which the effective age is going to be significant in one direction, turn to non-significant, and then flip. So in this case, it looks like the lower bound for the age slope, so scrolling back up here, is 6. So somewhere just, let me see, is it 9? 9.6. So basically the age slope starts being negative just after, since this is going backwards, this red line. And if I follow this out, where does it eventually become positive? Is at grip strength equals 18. So then the question is, how many people do we have in the sample that are that strong? So for the majority of the sample, the effective age is going to be significantly negative or non-significant. So anybody who is fewer pounds than 9, between 9 and 18 would be non-significant. Likewise, if I do the same process in the opposite direction, think about the effective grip strength as being moderated by age, then this is telling me that the effective grip is going to be significant below 70, non-significant between 70 and 82, and then significant past 82. So if I put those boundaries on my plot here, grip is going to be significant at basically any value. I just lost the numbers again, sorry. 82. So it will be significantly positive anywhere past 82, so a little bit past the blue line. Right here, it will turn to negative. And if I follow it into younger ages heading up this way, it will turn positive after age 70. So people younger than 70 would, damn it, turn negative. I've been doing this too long, sorry. Anyway, that's the boundary, but there's nobody in the sample that's that young. So these values have to be interpreted in the context of the distribution of the moderator. That would be the most useful way to report them. R has routines that do this as well. I found one within a package called Interactions. The call to it is Johnson-Neiman, which is, these are the originators of this technique. It's like really old. I don't remember how old, but it's very old. And people more recently have figured out how to hack that same idea for this purpose. And so this gives you the same regions of significance. So it tells you with respect to the centered variable where the boundaries are, and then it also tells you what the range of possibilities are in your data. So it combines those two pieces of information, which is helpful. One side note, it makes by default a plot of the regions of significance and the simple slopes, and that plot broke my computer. So I tried to run this a few times, and each time R just hung, and eventually I had to kill it manually and restart. So I turned the plots off so that it wouldn't break my computer. You can see if maybe yours has better luck. So that's it. That catches us up to where we were at the end of class, and then on Tuesday next week we will do the final model, and this is the model that will be most useful in helping you finish your first homework assignment. So until then, thanks for joining us. Take care, smash that like button, and hit subscribe.